What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 5, Section 2, Power Functions and Polynomial Functions. Let's do it. Explain the difference between the coefficient of a power function and its degree. So let's say we have a power function here, again, where we have a constant 4 and then a variable raised to a certain power. Let's say to the 5th. So this is a nice example of a power function. The coefficient is that value that's multiplying the leading term, right? So the coefficient in this case is 4, and then the degree is the value of that exponent, right? So this is a 5th degree, so the degree would be 5, boom, done. In general, explain the end behavior of a power function with odd degree if the leading coefficient is positive. So let's take an example of that. Let's say f of x equals a positive leading coefficient, let's just say 3, and then x to the 7th, okay? So this is what they're talking about with an odd degree. So what's the end behavior? By end behavior, they mean what happens as we go really far to the left and right of the graph, okay? Let's not worry too much about what it looks like on the inside, okay? It's just gonna be a bunch of stuff. It's gonna go through the origin. But as we go out to bigger values of x, let's say just go towards infinity, okay? As we go to these larger values of x, what's going to happen? If it's 10 to the 7th, that's like 10 million or whatever it'd be. It'd be like a huge number. 100 to the 7th, even bigger, right? So we're going up. We know that as we go to the right. What about when x's get really negative? Well, we know then the end behavior as we go to the left. Imagine negative 10 to the 7th. That's a huge negative number. Negative 100 to the 7th, another huge negative number, because a negative times itself an odd number of times is going to be negative as well. So as we go to the left, it's going to go down towards negative infinity, which means as x approaches infinity, the function value also approaches infinity. And as x approaches negative infinity, the function value approaches negative infinity. So there's your end behavior. Boom, done. What can we conclude if in general the graph of a polynomial function exhibits the following end behavior? So I'm going to kind of draw this out as I'm reading it. So it's saying as x approaches negative infinity, the function approaches negative infinity, which means we're kind of going like that as we go to the left. As x approaches positive infinity, we're also going to negative infinity for the function. So as we go to the right, it's also going down. And then whatever happens in the middle, it doesn't really matter. But what we can conclude, if this is indeed a polynomial function, we can conclude two things. Number one, this is an even polynomial degree, right? So it's got an even degree for the leading coefficient if this is a polynomial function, all right? So number one, it's got an even degree. Number two, since it's going down, down, left and right is going down, down, it means the leading coefficient must be negative. The reason why we conclude that the leading coefficient is negative is because it makes it so that as we go up or down, we're always going negative, okay? So think about, for example, if we had x to the 4th, right? X to the 4th, as x gets really big and as x gets really small, that's gonna be positive, positive. So the only way to make this even function go down, right, as we go to the right and the left is to throw a negative number on the front, because this is always going to be positive as we go to the right to infinity, and then you multiply by negative, it goes negative. Likewise, a big negative number to the 4th is also going to be positive, but you tag it with the negative, is negative. So there's your answer, boom, done. Here we're meant to identify this as either a power function or a polynomial function, or neither, but let's simplify this first. That 3 multiplies it, and then we have x to the 6th. So this means we have a single term raised to a power, which makes it a power function, boom, done. So this one is definitely not a power function, as it's not written in that format of like k to the x to the n or something, right? Like 3x to the 7th. That would be a power function. So it's clearly not that. Now, the question is this a polynomial? Well, this is actually not a polynomial. This is actually a rational function because it's something over something like this. We can't really simplify anything. So this actually falls into the category of neither, boom, done. So for this one, this would definitely not be a power function because, again, it's not in that format of a constant times x raised to some power, right? Again, like an example would be 2x to the 5th. So this is not a power function. Now, is it a polynomial function? A polynomial function would be variable raised to a power and multiple instances of that, something like 3x squared plus 2x minus 1, something like that. That would be an example of a polynomial. This is an exponential function, right? It's a constant raised to a variable. So this again would be neither, boom, done. So for this polynomial, we have negative 2x squared and 7. So the highest degree is right here, is 2. So we should rewrite this as negative 2x squared plus 7. Now I can say what my leading coefficient is as well as the degree. So the leading coefficient is this number in front of the term with the highest degree. So leading coefficient, is going to be negative 2, and the degree of this polynomial is this guy right here, which is a degree of positive 2. There's your answer, done. So for this one, we can simplify by FOILing everything and multiplying, and then we'll look at the polynomial and figure out the leading coefficient and the degree. So first I'm going to distribute this guy in here, and we got 4x minus x cubed, and then I'm going to multiply it times this binomial, and we're going to FOIL. So we got 8x squared plus 4x minus 2x times x cubed is actually negative 2x to the fourth, and then we've got negative x cubed over there. But what we really care about is the term with the highest degree, which is this term. Okay, I could reorganize it. Actually, you know what? I'm going to reorganize it. Let's make it negative 2x to the fourth minus x cubed plus 8x squared plus 4x. But I didn't really need to do that because the key is this guy. This is our term with the highest degree. So that means our leading coefficient is the coefficient of this, which is negative 2, and the degree is that degree, that exponent, and the degree, is going to be 4. Boom, done. For this one, we're going to determine the end behavior of this function, of this power function. So here's the deal. It's got a positive leading coefficient, okay? And that's because it's got an invisible 1 there. So it's a positive leading coefficient, and it's got a degree that is even. Okay, so we're going to look at these two factors right here, positive and even. So when a polynomial has a leading term with a positive leading coefficient and even degree, it's going to go up on either side, okay? And you can memorize these, right? If the leading coefficient is negative and it's even, it's going down. But this is the gist of it. And you can pretty quickly prove this by plugging in like 10, 20, 30, and you see it just gets really, really big. What about negative 10, negative 20, negative 30? Also is going to get pretty big. Same values, right? So, and then if we're going to put this into our nice terminology, we say as x approaches positive infinity, this is going up to the right, the function also approaches infinity. And then as x approaches negative infinity, meaning as it gets really, really small, the function value again approaches positive infinity. This is that up. So it's up to the right, up to the left. That's how you do it. Done. So for the end behavior for this one, we're going to recognize that our leading coefficient is that negative 1. Again, it's an invisible 1, but we got negative 1 for the leading coefficient, and then the degree is 4 here. But the most important thing is that it's even. That's the key. So we got a negative leading coefficient and we got an even degree. So when you have negative leading coefficient, even degree, you're going to look like this at the end behavior. It's going to go down. Now, if you want to verify that, you can just plug and chug some values. Imagine you're plugging in 10, 100, 1,000. You're taking all those to the fourth power, but then that negative always makes the final answer negative. So you're going to super low negative values, aka going down as you go bigger with the x values. Likewise, when you go negative x values, right? Negative 10, negative 100, negative 1,000, you're taking those to an even degree, to the fourth power. That's going to come out as an even number. Think about negative 10 to the fourth. That's going to be, 10,000 positive. Negative times negative times negative times negative, positive. So it's going to be a big positive value, but then you're tagging it at the end with the negative, which makes it, again, these really super negative numbers. So that's how we can verify the down. And then what we can say is as x approaches infinity, the function approaches negative infinity. Likewise, as x approaches negative infinity, the function, as we just mentioned, also again approaches negative infinity. Boom, done. So for this function, all we're doing is we're looking at the leading term of this polynomial, which is negative 2x to the fourth, which means we have a leading coefficient that is negative, and we have a degree that is even. So when you have a leading coefficient that's negative and an even degree, we're talking end behavior that is down. Again, you can verify this by plugging in 10, 100, 1,000. You see we get really negative numbers, like big negative numbers, if you will. Likewise, when you plug in negative 10, negative 100, negative 1,000, we're getting, again, these big positive numbers that at the end are going to be multiplied by negative 2. And it's going to be, again, these massive negative numbers. So we're going down and down. But you might say, like, what about the rest of these? Well, the thing is, the reason why we don't look at those is because as x gets really, really big or really, really small, meaning like negative 100, negative 1,000, these guys kind of don't have that much of an effect. Imagine a million plugged in for x. A million to the fourth power is so much bigger than a million squared. So these kind of become irrelevant. That's why we look here. So now we've kind of confirmed that we know that this is going to go down, down, meaning as x approaches positive infinity, meaning going to the right, the function is going to approach negative infinity. It's going to go down. And also as x approaches negative infinity, as we mentioned, the function is still going to go down. It's still approaching negative infinity. Boom, done. For this one, we're going to start by distributing and simplifying. So we're going to have 2x to the fifth minus x cubed plus x squared. Now, when we're trying to determine end behavior, we really only care about that leading term. And the reason why is because as x gets really, really big, these kind of don't matter so much. As x gets really, really small, meaning negative 100, negative 1,000, negative a million, again, these are kind of dwarfs. So we're just worried about this. And what we have is a leading coefficient that is positive, and then we also have a degree that is odd. So when you have a positive leading coefficient and an odd degree, what we're looking at is we're looking at down to the left and up to the right. The middle part doesn't really matter, but this is the key. Now, why is this? Again, think about only this term, and if you plug in big numbers like 100, 1,000, a million, you're getting huge positive numbers, right? Because you're just doubling whatever you get. Likewise, when we plug in negatives like negative 10, negative 100, you're taking that to the fifth power. Any negative that's raised to an odd degree is going to be odd. Think about negative 2 to the third power, right? If I have negative 2 to the third power, negative 2 times negative 2, that's positive 4, times another negative 2 is a negative 8. It ends up negative. So as we go to the left, we're going to get these crazy big negative numbers, meaning it's going down. So for our end behavior, we have as x approaches positive infinity, the function value approaches positive infinity. As x approaches negative infinity, going to the left, you can see that the function value also approaches negative infinity. So it's down to the left, up to the right, boom, done. For this question, it wants us to find both the t-intercepts, aka the values of t that make the function go to 0, as well as the y-intercepts, or function intercepts, if you will, and that's when you plug in 0 for t. So let's get both of those. So the t-intercepts can be found just by looking at this in factored form, meaning what will make this go to 0 will make everything go to 0, and that's going to be 1. We've also got, for this one, that would be negative 2, right? Negative 2 plus 2 is 0. And last but not least here, we would have a t-value of 3. So those are our t-intercepts. For our y-intercept, are really the function intercept, but this is how they put it in the back of the book, right? Because it's a function of t. But to get that, we're trying to figure out the function value when t is equal to 0. Okay, so you just plug in 0 and you solve. So you get 2, 0 minus 1 is negative 1, 0 plus 2 is 2, 0 minus 3 is negative 3. So that's negative 2 times 2 is negative 4, times negative 3 is positive 12. There's the answer. Boom, done. For this one, as we find the x-intercept first, I'm going to start by factoring. So you can see that this is a difference of squares. The way we factor that is the square root of the first, which is x squared. We put that here and here. Then the square root of the second, which is 4, right? Square root of 16 is 4. And then we alternate with the plus minus. And you can see if you redistributed, you'd end up with x to the fourth minus 16, right? If we FOILed this out. So that's kind of the key indicator that we got it right. But then we see we have another difference of squares, so we can factor again. And with this one, it's x minus 2, right? Square root of each, x plus 2. Okay, and now we can get those x-intercepts. So the thing is, when we have x squared plus 4, there's actually not going to be a real x value. There's an imaginary, but not a real number that is going to zero this out. So this little binomial here does not produce an x-intercept, but this one does and this one does, because it zeroes out at positive 2. So we have an x-intercept at positive 2 and one at negative 2. So these are the x-intercepts. And then when we come for the y-intercept, what we're doing is we're plugging 0 in for x, right? Just like for the x-intercept, 0 is basically your y value. For the y-intercept, 0 goes in for x. So you plug it in. 0 to the fourth power is 0 minus 16 is negative 16. There are your intercepts. Done. For this one, to find the x-intercepts, we're going to start off right away factoring that trinomial. So it's x squared minus 2x minus 8, meaning we put the x here and x here. What two numbers multiply to negative 8 add to negative 2? That would be negative 4 and positive 2. Multiply to negative 8, add to negative 2. So we factored this correctly. Now we're going to find the x-intercepts. So again, for the x-intercepts, it's what's going to zero this out, meaning what's going to produce a y value of 0. So what you'll notice here is there's actually going to be 3 values of x, right? First, I can make x 0. That's going to make that one 0. It's going to zero everything out. So 0, 0 is one x-intercept. We also have, for this one, what's going to zero that out? Positive 4. And then what about this one? It's going to be negative 2, right? Negative 2 plus 2 is 0. Now, when we come to the y-intercept, you notice we already know the y-intercept. The y-intercept is when x equals 0. Well, guess what? It's that point right here. And we're only going to have one y-intercept for a proper function, right? So this is our y-intercept as well. It kind of doubles as an x and a y-intercept. So there's your answer. Boom, done. So for this one, it says to determine the least possible degree of the polynomial function. So the way we do this is we look at the number of turns. So what do I mean? I mean going from increasing to decreasing, aka positive slope to negative slope. So you see here, I see one turn, right? That's 1. And then I see it turn again, right, from negative to positive. So that's 2 turns, which means the least possible degree has to be 1 more than the number of terms, which means it is 3. Boom, done. For this one, once again, we're going to count the number of turns, aka going from positive to negative slope or vice versa. So we got, check it out, negative goes to positive, that's 1 turn. Positive goes to negative, that's 2 turns, right? Negative goes to positive, that's 3 turns. Positive goes to negative, that's 4 turns. So that's 4 terms, meaning the least possible degree is 1 more than the number of terms, aka 5. Boom, done. For this one, we're going to take a look at the number of turns. We've got 1 turn, and a turn means going from positive to negative slope or vice versa. So we're going positive to negative, that's 1, negative to positive, that's 2. And so since there are 2 turns, it must be at a minimum 1 more than the number of turns, aka a minimum of a 3rd degree. Boom, done. For this one, we're going from positive to negative, that's 1 turn. Negative to positive, that's 2 turns, right? So again, to get the degree, we need to get the number of turns and then add 1, right? And turns are, again, going from negative to positive slope or vice versa. Another turn, positive to negative, that's 3. Another turn, negative to positive, that's 4. So if there's 4 turns, it must be at least 5th degree. Boom, done. This question asks if this is a graph of a polynomial, and if so, what is the least possible degree? And this is definitely a polynomial. It's continuous. You see how it kind of goes along. It's got these turns. So this is the indication that it is indeed a polynomial. And but to get that least degree, we're going to look at the number of turns. So I see 1 turn right here, and it's just barely a 2nd turn, right? You can see it just dip down a tad bit and then goes up again. So that's 2 turns, which means I would say, yes, this is polynomial with a minimum of, again, 1 more than the number of turns, aka a least possible degree of 3. Boom, done. For this question, I would say, yes, indeed, it is a polynomial. It's nice and continuous. It's got a single turn point. So I would say, yes, this is a polynomial. And since we got 1 turn, right, going from negative to a positive slope, the least possible degree is 1 more than the number of turns, which is 2. So there's your answer. Done. So for this function, this is a nice, smooth, continuous function. I would say, yes, it is a polynomial. Now, it's kind of interesting because there's not really a turning point. It kind of looks like it turns here, but then it just never seems to go negative, right? The slope just continuously is positive. So we actually have no points of turning, which means the least possible degree technically is 1, right? Using the number of turns, which is 0 here, plus 1 to get the least possible degree. So there you go, boom, done. For this graph, it's nice and smooth and continuous. So I would say, yes, it is a polynomial function, and it's a line, right? This is a linear function. So what are the number of turns? There's no turns. It's just nice, straight, consistent, positive slope, which means there's 0 turns. So to get the least possible degree, you add 1 to that. So the least possible degree is a degree of 1. Boom, done. So for this question, it asks to make a table to determine the end behavior. So I'm going to kind of choose, this is arbitrary, right? We can choose what values we like. But I'm going to choose the values that are at the end of the book and kind of set it up. We're going to plug and chug, and we're going to see what we get. Then we're going to talk a little bit about what end behavior really means. So as my inputs, I've got 10 and 100, negative 10 and negative 100. So why did I choose those values, or why did the back of the book choose those values? Is because what we're trying to see for end behavior, just like the name indicates, we're trying to see what happens as x goes off into infinity, the inputs go off to infinity. What's happening to the behavior of the function? Is it trending in one particular direction? Likewise, what happens as x goes towards negative infinity? So those are the 2 end behaviors, right? Going positive infinity, negative infinity. So now we're going to plug and chug and we're going to see what we get, and then we're going to sort of make a prediction about the end behavior. So when I plug in 10 for x, 10 to the fourth power is 10,000 minus 5 times 100, so that gives us 9,500. Again, you can use a calculator for this part if need be, just to plug and chug. And then if we plug in 100, we get a much larger number, which is 99,950,000, huge number. Okay, but is this enough to sort of give us an indication? Yeah, it sure is. It sure seems like when we plug in when the x values get bigger and approach infinity, the function value is also approaching infinity. You could probably plug in 1,000, 1,000,000, 1,000,000,000. Okay, and it's just f of x is going to keep on rising to the stars. And really, you don't even need to plug these values into the table. You can kind of look at the leading term and be like, well, of course, as x to the fourth, as x gets really, really big, x to the fourth is also going to continue to get really, really big because it's just x times itself 4 times. So that's kind of the shortcut, but this is a nice way to verify it. Now, if we plug in negative 10, the interesting thing is that because it's to the fourth power here and squared here, we're actually going to get the exact same value, 9,500. And here we're going to get the same value for negative 100 as we did for positive 100, which is 99,950,000. So what we can see is as x approaches infinity, the function value seems to also approach infinity. Likewise, as x approaches negative infinity, we've now shown and proven, and we could deduce this if you just look at x to the fourth, you plug in bigger values, more negative values, it's still going to get bigger and go towards positive infinity, right? So as x approaches negative infinity, the function value again approaches positive infinity. There's your end behavior, boom, done. So for this one, once again, we're going to choose values based on what they've provided in the back of the book for this table, but it's arbitrary. You don't have to choose these values, but we're going to do exactly what they did. And just as a quick recap, when we're talking about end behavior, we're seeing where is the function going as x gets really, really big, aka as x approaches infinity, and as x gets really, really small as it approaches negative infinity. So this table is going to give us an idea of where the function is going at the end, at the outer limits of x. So we're going to plug and chug, so you can use your calculator, plug 10 in, you get 10 minus 1, which is 9, times 10 minus 2, which is 8, times 3 minus 10, which is negative 7. And when you multiply this out, we get negative 504. When you plug in 100, it's 99 times 98 times negative 97, which gives a value of negative 941,094. So you can see we get a negative output and then a much larger negative output. So that already gives us a nice idea of where it's going, but let's now plug and chug for negative 10. So we get negative 10 minus 1, which is negative 11, times negative 10 minus 2, which is negative 12, times 3 minus negative 10, that's basically 3 plus 10, which is 13. So a negative times a positive, of course, is going to give us a positive value of 1716. Now, when we plug in negative 100, you can use a calculator. We get a pretty big number, which is 1,061,106. Let's put a couple commas in like so. And we now get an idea, right? As this gets bigger, it seems sure to be approaching negative infinity, right? 10, 100, we imagine 1,000, 1,000,000. It's just going to go deeper and deeper into the negatives. Conversely, with the negatives, as they seem to get deeper into the negatives, technically smaller, but like bigger negative numbers is kind of like one way to think about it. Negative 1,000 would probably be bigger. Negative 1,000,000 would be a bigger output. So we have as x approaches in positive infinity, the function value seems to be going the opposite way towards negative infinity. And then as x approaches negative infinity, the function value is instead approaching positive infinity, boom, done. So for this one, we're meant to use a graphing calculator and then based on the graph, determine the intercepts and the end behavior. So let's do that in Desmos now. So what we see here are the intercepts kind of marked out like this and this. So we've got an x and a y intercept of 0, 0, because again, when it goes through the origin, it's hitting both axes. So, and then we have an additional x-intercept at 2, 0. And then I can see the end behavior, meaning what happens as x gets more and more negative, goes to the left? Well, it sure seems to be approaching positive infinity, right? Going up and up with no end in sight. Likewise, as x seems to get really, really big on the positive side, it again seems to be going towards positive infinity. So the end behavior as x goes positive and negative, the function value is going positive. So let's write that out. So as we mentioned for the x-intercepts, we saw at the origin 0, 0, and then we also saw at 2, 0, and that y-intercept is the same as the origin, right? Again, this origin intersection doubles as an x and a y-intercept. And then we have the end behavior, and we said as x approaches negative infinity, the function value was going up to positive infinity. Likewise, as x approaches positive infinity, the function value was also going towards infinity. Boom, done. So for this one, we're meant to graph it and then look at the x and y intercepts and check the end behavior. So let's do that now in Desmos. So for this one, I adjusted the scaling a little bit so we could see it clearly, but check this out. Look at our intercepts. We got the origin, we got another x-intercept at 5, 0, and another one at 7, 0. Now, that origin intersection is both an x-intercept and our y-intercept. And then we also have additional x-intercepts at 5, 0, 7, 0. If we talk about end behavior, look at this. As this thing is approaching negative infinity, the x values is going to the left. Look, it's going down. So we can see that as x approaches negative infinity, the function is also approaching negative infinity. Conversely, on the right side, as x gets bigger and bigger as we go to the right, okay, x is approaching the function value, is approaching positive infinity. It's going up and up and up, right? So we have as x approaches positive infinity, the function also approaches positive infinity. So let's write that out. So for the x-intercepts, we have 0, 0, 5, 0, and 7, 0. And then again, that origin, that's also our y-intercept at 0, 0. And then we have as x approaches negative infinity, as we recall, the function value, going to the left, the function value was also approaching negative infinity. And then as x approaches positive infinity, aka as we go to the right, the function value was going up, aka approaching positive infinity. Boom, done. For this one, we're meant to put it in our graphing calculator and then check the intercepts as well as the end behavior. So let's do that now in Desmos. So once again, I've adjusted the scaling so we can see a nice representation of this function. And I'm seeing 3 x-intercepts. I'm seeing negative 4, 0, 0, 0, and 4, 0. Again, that's where it hits the x-axis. And I'm only seeing 1 y-intercept, and that also is one of our x-intercepts at 0, 0. It's hitting the x and the y-axis simultaneously. Now, as we look at end behavior, as the function goes to the left, aka as x approaches negative infinity, the function value is going down. So as x approaches negative infinity, the function is also approaching negative infinity. Conversely, as x approaches positive infinity, meaning as we go to the right, the function value is also increasing, going up, meaning as x approaches positive infinity, the function is also approaching positive infinity. So let's write that out. So the x-intercepts are negative 4, 0, 0, 0, and 4, 0. And that 0, 0 as the x-intercept doubles as a y-intercept as well. And then we say as x approaches negative infinity, the function value was also going down and approaching negative infinity as well. And then as x approaches positive infinity, the function value was also approaching positive infinity. Boom, done. For this one, we're meant to graph it in Desmos and then check the x-intercepts, y-intercept, and look at the end behavior. So let's do that now. So with this one, we can see that the x-intercepts are at negative 3 and positive 3, 0. And the y-intercept is down here at 0, negative 81. If we look at the end behavior, as x goes to the left, aka as x goes towards negative infinity, the function value is going up, meaning the function value is approaching positive infinity. And likewise, as x goes to positive infinity, meaning to the right, the function value is once again approaching positive infinity. So let's write that out. So our x-intercepts are at negative 3, 0, and 3, 0, and that y-intercept was at 0, negative 81. And then for the end behavior, as x approaches negative infinity, the function value was increasing, meaning going towards positive infinity. And as x approaches positive infinity, it was going up both sides. So once again, the function value is approaching infinity. Boom. For this function, we're meant to graph it in Desmos and then look at the intercepts and the end behavior. So let's do that now. So here we can see the x-intercepts are at negative 3, 0, 0, 0, and 5, 0. Okay, and that 0, 0 is also our y-intercept. It's also where it hits the y-axis, right? And then let's look at the end behavior. As x goes towards negative infinity, the function's going down. So it's also approaching negative infinity. As x goes to the right, meaning as it approaches positive infinity, the function value is going up. So that's also approaching positive infinity. So let's write that out. So here we got negative 3, 0, 0, 0, and positive 5, 0. And again, that's also our y-intercept right here. So we got 0, 0. And then we said the end behavior was as x approaches negative infinity, the function value was also approaching negative infinity. Conversely, as x approaches positive infinity, as we went to the right, the function was going up, meaning the function was approaching positive infinity, boom, done. So for this one, we've got some information about the y-intercept as well as the x-intercepts and the degree, and we can use that to piece together a function for all these components. So first of all, I know if the x-intercepts are -2 and 2, I imagine in factored form, it's going to be x plus 2, that gives me that 0 of -2, and then x minus 2, which gives me that 0 of 2, right? If I plug in 2 here, it's going to get 0, which we want. And if I plug in -2 here, we're going to get 0. Everything's going to 0 out, which we want as well. And the cool thing is, it also says, we don't know, maybe there's a leading coefficient, but it did say assume the leading coefficient is 1 or -1. So we don't know which it is, but the cool thing is, as is, if you plug in 0, which is how you get the y-intercept, you get 2 times -2, which is -4, which means we don't have to change anything. This function is perfect. The only thing to simplify it or to put it into kind of a nice standard form is just a FOIL, like boom, 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 boom. So we get x squared minus 2x plus 2x. Those cancel out, right? They add together and cancel out. And then 2 times -2 is -4. So our function would be x squared minus 4, boom, done. So to start this one off, we have two x-intercepts here and here. We also have a y-intercept at 0, 0, which is the same as one of the x-intercepts. Again, as I mentioned in a previous explanation, if you have an x-intercept at the origin, it also doubles as your y-intercept. So to put these together in our nice binomial format, it's x minus that x-intercept, x minus that x-intercept. So this in and of itself should be enough. However, it does say that the degree is 3. So if I multiply this out, I'd get x to the second power, meaning a degree of 2. So to get this to the third degree, I can either simply just square this one. I can't add another x minus 5 or x minus 7 because it doesn't say that there's another x-intercept, and that would create a new x-intercept. So I've got to square one of the existing ones. So I could do that one, or I could square this one. So again, both answers will be good. I'm going to square this one because this is what they did in the back of the book, and I'm going to show you how this works. So x minus 0 is x, and then x minus 2 squared is x minus 2 times x minus 2, and then we can FOIL this out. I'm going to FOIL this out first. It doesn't matter which way you go, or I could distribute the x in, but let's do it like this. So this gives me x squared, then it's minus 2x minus 2x, which is minus 4x, and then -2 times -2 is positive 4. And then all of this times x, and then as we distribute that x at the end, we get a final function of x cubed minus 4x squared plus 4x for the win. Boom, done. So for this one, we've got a y-intercept of 0, 1, and it says there's no x-intercept. So what does that mean? That means if we were to graph this out, it's looking like we're going through here, let's say a 0, 1 for the y-intercept, and it's never hitting the x-axis, no x-intercept, meaning it's probably going up and up in both directions, never going down. And that makes sense because a degree of 4, an even degree, means the end behavior at the right is going up, and the end behavior at the left is also going up. This is further confirmed, by the way, by this. This is literally the end behavior. As x approaches negative infinity, it goes up. X approaches positive infinity, the function goes to positive infinity. So we just verified that. All right, now how do we put this together? So no x-intercepts and a degree of 4. So one possibility is we say x to the 4th, there's our 4th degree polynomial, and it says a y-intercept of 1, meaning if I plug 0 in for x, I should get 1. Well, here if I plug 0 in, I get 0. But if I just add 1, meaning I shift x to the 4th up by 1, I've got a perfect example of a function that fits the bill. Boom, done. A cube has an edge of 3 feet. The edge is increasing at the rate of 2 feet per minute. Express the volume of the cube as a function of m, the number of minutes elapsed. So we could say volume as a function of m equals, and before we do that, let's draw out a cube. And again, a cube, all the side lengths are equal. So this is equal to this, right? Length, width, and height are all the same. And they say edge up here, right? That's kind of what I meant with side. So all the edges are equal. They're all 3 feet. And each of these appear to be increasing at 2 feet per minute, meaning for every minute, it's going up by 2, right? At 1 minute, it would be 5. At 2 minutes, it would be 7, etc. And so all of these side lengths can be expressed like that. So to get the volume, it's, think about volume of a regular cube. It's the side length or the edge, 3 plus 2m in this case, times itself again, length times width times height, or to the third power. Now, if we want to FOIL this out into a nice polynomial, let's do so as follows. So we've got this cube, so we're going to FOIL like so, boom, boom. We got 3 times 3 is 9 plus 6m, 3 times 2m, and then another 6m, 3 times 2m, so that's 12m, and then plus 4m squared. And then again, times this last binomial, so now we'll do another foiling, kind of like 9 is going to go here and here first. So we got 27 plus 18m. Then we have the 12m hitting that and that, which is 36m plus 24m squared, right? 12 times 2 is 24. And then last but not least, 4m squared times the 3 and times the 2m. So we have 4 times 3 is 12m squared, and then 4m squared times 2m is 8m cubed. And then now as we combine like terms there, and then put the kind of leading term first, we're going to rewrite it as 8m to the third power, and then we're going to go in decreasing order of degrees. Then 24 plus 12 is 36m squared, and then 36 plus 18 is 54m, right? And then plus that remaining 27 at the end, and there is my final function. Boom, done. An open box is to be constructed by cutting out square corners of x-inch sides from a piece of cardboard 8 inches by 8 inches, and then folding up the sides. Express the volume of the box as a function of x. So first, let's draw this out. So we're starting here with 8 inches by 8 inches, and then we're cutting out these little squares like so. And all these squares have a side length of x. And then when we fold it up, what we're doing is we're really creating a rectangular prism with no top, okay? So you can kind of imagine everything folding up. And then these heights are actually what x is. You see, as you kind of fold this side up, that x length is actually going to be the height. So we got x, for all of this. And then what is this remaining segment here? Really, it's this part right here. That segment is going to be now this new edge, which is what? It's 8, was a full 8, but then what are we minusing? We're minusing an x and an x on both sides. So now this new side length is 8 minus 2x. And since it's a square, it's the same for this side, aka, if that's the length, this would be the width, right? Again, 8 minus 2x. And so now we have all our dimensions. We can express this volume as follows. So it's length, which is 8 minus 2x, times width, which is 8 minus 2x, and then times the height, which is x. And then if we want to put this in that nice simple format of a polynomial, we're going to FOIL. So first we have 8 times 8, which is 64. Then we have 8 times negative 2x, which is negative 16x. And then negative 2x times 8 is again negative 16x, which is negative 32x. And then negative 2x times negative 2x is positive 4x squared. And then we still have to distribute that x on the outside. So this, as we distribute it in, it becomes 64x minus 32x squared plus 4x cubed. Last but not least, we're just going to write it in that nice format with the leading term first, then second degree, then first degree. So we have 4x cubed minus 32x squared plus 64x for the win. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.